Okay, hi, and welcome back. So in today's video, we're going to be exploring linear algebra a little bit, and in particular, we're going to be looking at matrices and how to compute the inverse of matrices. So a large focus of this video will be on computing inverse matrices, but we'll also take a brief exploration into seeing what inverse matrices can be used for. There are numerous applications of them, but we'll look at maybe one, maybe two, and we'll see how we go from there. Before we get into this lecture, I just want to quickly apologize for this earbud setup that you might see. This is solely for the purpose of audio reasons. The camera doesn't pick up very good audio, and this is the only microphone I have, so this is what we're going to work with. With that said, let's get into today's lecture. So we are talking about inverses of matrices, and the idea of this is we're going to take as an input some n by n matrix, which we'll call A, and our goal is to output an n by n matrix, which we call A inverse, and it's denoted with this -1 power, A inverse, A to the power of -1, but we never say to the power of -1, we just say A inverse. Notice that both of these matrices are n by n matrices, so we're going to be taking inverses of square matrices, and our inverse should also be a square. And we'll see that not all square matrices have inverses. Okay, so our output has to be this matrix A inverse, but what's special about A inverse is if we were to compute A multiplied with A inverse, that product should equal A inverse multiplied with A, but overall the product should equal the identity matrix, which is an n by n square matrix. So recall the identity has ones along the diagonal and 0 everywhere else. So we want that product to yield us the identity matrix, an n by n square identity matrix. And as I alluded to earlier, not all square matrices will have inverses, and in fact we have this proposition that states a square n by n matrix has an inverse if and only if its rank is n. So this means if we have a square matrix, then it'll have an inverse if its rank is n, and the converse is also true. So that's that to be aware of. Here is the procedure that we'll be following. In the first step, we're going to take our matrix that we started with and augment the identity matrix to the right of it. From there, we're going to follow our standard row reduction procedures to obtain a row reduced echelon format on the left-hand side. And in fact, we're going to do that until the left-hand side is the identity matrix. Once we do that, the right-hand side, which is basically what we originally augmented after row reduction, that will be A inverse. So visually, we start with A, we augment the identity to the right side of A, we perform row reduction until the left-hand side is the identity, and our right side will be A inverse, it just so happens. Okay, so let's suppose we see a problem like this, and you know it's not uncommon to see these kinds of things, and I'm sure you've seen it in elementary school and middle school where you have two equations with two unknowns and you learned how to isolate for one variable, do some sort of substitution, things like that. But in the real world, it's not always just two variables and two unknowns. Sometimes it's three variables and three unknowns, or hundreds of variables and hundreds of unknowns, and nobody wants to sit around and just isolate variables for their entire life. So we need a way to solve it quicker. And in fact, there's many, many ways to solve this system of equations here, but we're going to see a cool way of doing it using inverse matrices. But first, we need to actually learn how to compute inverse matrices. We've done the procedure. Let's do some examples. All right. So our first example says that if A equals 2764, what is A inverse? And we're going to follow the same procedure that is outlined up there. And first we'll augment the identity matrix. So let's do that. We start with 2764 on the left-hand side. We will augment it. I'll throw in this bar here to create the separation. And we throw in the identity matrix, which is a 2 by 2 matrix in this case, since our matrix was 2 by 2 to start with. Now we just have to do a bunch of row reduction until we get the identity matrix on the left-hand side. And the way we can do this is, I see a 6 here, I see a 2 here. Well, if I were to make this a 6, then I could get rid of this 6 pretty easily, because I want this term to be a 0. So what I'll do is I will multiply row 1 by 3. So the second row stays as is, 6, 4, 0, 1. And the top row will be multiplied by 3, 6, 21, 3, 0. Okay, so now I can subtract R1 from R2, where R1 is row 1, R2 is row 2, because that would make this 6 a 0. So let's do that. Row 2 is equal to row 2 minus row 1. The first row we're not changing, so we'll keep that as is. 6, 21, 3, 0. And now we subtract, so 6 minus 6 is 0. 4 minus 21 is negative 17. 0 minus 3 is negative 3. 1 minus 0 is 1. Cool. And remember, our goal is to get the identity matrix here. So we have the 0 here. We can make this a 1 by dividing the first row by 6, and we can make this a 1 by dividing the second row by negative 17. So let's do both of those at once. So row 1 equals row 1 divided by 6, and row 2 equals row 2 divided by negative 17. So if we divide the first row by 6, the first term becomes a 1. 21 divided by 6, both share a common factor of 3, so this becomes 7 halves. 3 divided by 6 is a half, and 0 divided by 6 is 0. For row 2, we're dividing by negative 17, so we have 0, 1. Negative 3 over negative 17, I'll just make that 3 over 17, keep it positive. 1 divided by negative 17 is negative 1 over 17. And now we're almost there. We just have to do row 1 minus 7 halves of row 2. Oh gosh, I can't even lift the thingy here. I have to squat down. Will it pick up on camera? Yeah, I think it will. Okay. So we're going to do row 1 equals row 1 minus 7 halves of row 2. So the first term stays as 1 because we're subtracting 7 halves of 0. Actually, we'll just put down the second row there because we know it's going to remain unchanged. 3 over 17, negative 1 over 17. This term becomes 0 because 7 halves minus 7 halves times 1 is 0. Now we have to figure out this term, and I'll do some math over here and then bring it over there just so we can view this. So that missing term, the first missing term, is going to be 1/2 minus 7 halves of 3/17. Okay, let's see. This denominator will be a 34, so let's make this a 34. So it's 17 over 34 minus 21 over 34, which is equal to negative 4 over 34, or negative 2 over 17. So this term becomes negative 2 over 17. And then we have one more term. So let me just erase this and do the same thing. Except now we're doing 0 minus 7 halves of negative 1 over 17, which is equal to 7 over 34. And well, we're basically done because we have the identity matrix here. So this is saying that A inverse is equal to negative 2 by 17, 7 over 34, 3 over 17, and negative 1 over 17. Which is fine. We see that all of the terms are divided by 17 or 34. So let's factor out a 1 over 34 term just so we have integer things in our matrix. So this is 1 over 34 times, well, this should be negative 4. This should be a 7. This will be 6. And this will be minus 2. And so yeah, we're done. And maybe that's correct. In fact, we'll check to make sure our answer is correct. But before we check to make sure our answer is correct, let's take a look at A and A inverse. Ignoring the 1 over 34 factor, these two matrices are pretty similar. We see a 7 here and a 6 there, and there's a 7 there and a 6 there. there's a 2 up here and a -2 here and a -4 and a -4, so they swapped and got negative signs in front of them. Is that a coincidence, or is there something actually going on? We're going to figure that out really shortly. Okay, so let's check to make sure our answer is correct. And in order to check that, we will simply compute the product of A inverse with A and see if it equals the identity. We could do A times A inverse, but I'm choosing to do it in this direction because when we write it out, this is what we just computed for earlier. We have this 1/34 on the left, and that way we can just multiply these two and then take care of the 1/34 earlier. So this is A inverse, which we just computed. That's A. Let's do this matrix multiplication. So this will result in a 2 by 2 matrix here, because both of these are 2 by 2. So to get the top left term, we multiply this row with this column. So -4 times 2 is 8, plus 7 times 6 is plus 42. So 42 minus 8 is 34. Now to get this term here, we do this row times this column. -4 by 7 is -28, plus 28 gives us 0. For this term here, we do this row by this column. That's 12 minus 12, 0. And for the last term, we do this row by this column. 42 minus 8, 34. When we throw in our fraction on the outside, we get the identity. So our answer is indeed correct. Let's try a different example. Okay, so now our second example will be with this matrix. A equals A, B, C, D, a generic 2 by 2 matrix. What's the inverse of A? So we'll solve this in a very similar way that we did the first problem, except now we don't have numbers to work with, we have letters. So we will start by augmenting the identity matrix to it. And then we'll row reduce. So I'd like a 1 here, so I can divide the first row by by A. And I'll try to do this row reduction a little bit quicker than before. Hopefully you're familiar with row reduction. 0, 1. Now I want to make this C a 0, so I can subtract C copies of row 1. So row 2 is equal to row 2 minus C times row 1. So the first row will stay as is, 1 B over A, 1 over A, 0. And then the second row, C minus 1 times C is 0. D minus C times B over A is literally D minus C times B over A. Can't really reduce that anymore. 0 minus C times 1 over A is negative C over A. And 1 minus C times 0 is thankfully just 1. Okay, we'd like to get a 1 here. So it's a little bit nasty, but why don't we just divide this entire row by that quantity? So we'll do row 2 divided by D minus CB over A. So the first row remains as is, 1 B over A, 1 over A, 0. The first term of the second row stays 0. Second one goes to 1. For this one, let's just do a little math over to the side. So we're doing negative C over A divided by D minus BC over A. We can multiply the numerator and denominator by A. That cancels this A with this, and that with that, but we have to throw in an A here. So this is negative C over AD minus BC. Negative C over AD minus BC. And for the last term, we're doing 1 divided by D minus BC over A. Again, multiply the numerator and denominator by A, and we get A over AD minus BC. A over AD minus BC. Did not give myself enough room there. But now we're pretty close. Let's see. We just need to make this a 0, so we'll subtract B over A copies of row 2 from row 1. And I'm going to do it right below it. So row 1 minus B over A copies of row 2. So row 2 stays the same. This is negative c over AD minus BC. And this is A over AD minus BC. This first term stays as a 1 because we're subtracting a form of 0. B over A minus B over A times 1 is simply 0. Can do a little bit of math for this last term here, or these last two. So this term will be 1 over A minus B over A times negative C over AD minus BC. Okay, so let's multiply this. We'll common denominatorize it, so we'll multiply AD minus BC over here. So this is AD minus BC over A times AD minus BC. That's this term. We're subtracting from that B times negative C, which is minus BC. So we'll make this a plus sign, and in the denominator we still have AD minus BC. That cancels with that. And we're left with AD over this. So in fact, let's just ignore this term entirely. The A's cancel, and it's D over AD minus BC. So this is D over AD minus BC. And the last term, well, I won't really waste your time on that. I think you can try to figure that out on your own. This will be negative B over AD minus BC. And so we've computed the inverse. I'm just going to erase some of what we had here. We said that A inverse is equal to, and what I'm actually going to do is I'm going to factor out this 1 over AD minus BC. And then we're left with D negative B, negative C A. And that is your generic form of the inverse of a 2x2 matrix. And what's especially nice about this is that this AD minus BC term is quite familiar, because the determinant of A is equal to AD minus BC. So we can swap this out with just the determinant of A. So if we recall the first example, we had this as our matrix A, and we said that A inverse was equal to this. It's not quite that, right? Here we see that D should be the first element, which would mean that it should be 4. Negative B, instead of positive 7, it should be a negative 7. And same thing with C and A. They're all off by a factor of negative 1. So maybe this should be negative 1 over 34, and then change these around. And indeed, that's exactly what we need to do to match that, because the determinant of this is equal to 2 times 4 minus 7 times 6, which is equal to negative 34. And now we've matched it. Let's do one more example, and then we'll wrap up. So now we're going to deal with a 3x3 matrix. 1, 1, 1, 1, 2, 4, 1, 4, 9, but the procedure is the same. I erased everything because I wanted more room. So the first thing we'll do is augment the identity. Now it's the 3x3 identity matrix. And then we'll row reduce. So I have this one here, which I want to keep, but I want to make these two a 0. So we'll do row 2 minus row 1, and we'll also do row 3 minus row 1. So just expedite the process a little bit. First row stays the same. Second row we get 0, 1, 3, negative 1, 1, 0, and then we get 0, 3, 8, negative 1, 0, 1. Cool. This is a 1 as it's supposed to be. This should be a 0, and that should be a 0. So what I'll do is row 1 minus row 2, and then I'll do row 3 minus 3 copies of row 2. So row 2 is going to stay the same, since we're not doing any operations on it. Now we'll do row 1 minus row 2. So this is 1, that's 0, that's minus 2. This is 2, minus 1, 0. I hope I'm doing that correctly. that minus that. Yeah, that looks right. And then we'll do row 3 minus 3 copies of that. So it'll be 0, 0, negative 1, minus 3 copies of that would make it a positive 2, minus 3, and then 1. And we want this to be a positive 1, so let's just multiply this row by minus 1, and I'll write it here, just so that way if you're keeping track, you know what's going on. And we're pretty close, we just need to make these two terms zeros. So we'll do row 2 minus 3 copies of row 3, and row 1 plus 2 copies of row 3. The last row will stay the same. The second row will become 0, 1, 0. Negative 1 minus 3 times negative 2 becomes 5, I believe. 1 minus 3 times that is negative 8. 0 minus 3 times that is positive 3. And then in the top, we're adding 2 copies of row 2. So this goes 1, 0, 0. 2 plus 2 times negative 2 is negative 2. This is so difficult. Minus 1 plus 2 times 3 is 5. And then this last one should be minus 2. So with that, we're saying that A inverse is equal to negative 2, 5, negative 2, 5, negative 8, 3, negative 2, 3. Or sorry, wait, what? I feel like, yeah, this is supposed to be a negative 2. Whoops. Minus 1. And let's just check to make sure we're correct. So we'll multiply this by A on the right, which was 1, 1, 1, 1, 2, 4, 1, 4, 9. And this should yield us a 3 by 3 matrix. First element is this row by that column. Minus 2 plus 5 minus 2 is 1. Minus 2 plus 10 minus 8, 0. Minus 2 plus 20 minus 18, 0. And then you can just trust me that this is correct. And there we go. That's a 3 by 3 matrix example. But I don't want to end just yet. Remember at the start we were looking at these equations and I was saying, oh, maybe I'll show you a cool way to do this with inverse matrices. And that's exactly what we're going to do now. This system of equations can be represented as a matrix equation with multiplication and some sort of equality. So what we'll do is we're going to represent the coefficients as a 3 by 3 matrix. And then we see that x3 is repeated, x2 is repeated, x1 is repeated. So we're going to think of multiplying that matrix with a vector of x's, and that should equal this. So let's just write it out. So right now I'm just writing the coefficients as they appear. So here we have a matrix equation which I claim represents that system of equations. And indeed, if you were to perform this multiplication, the first thing you would do is multiply the first row by this column vector. We would get x1 plus x2 plus x3. And I'm saying this should equal 4. And then the second term, you do this row by the column. So x1 plus 2x2 plus 4x3 equals 4. So we can see that this is exactly that. And our goal is to compute this vector, x1, x2, x3. Well, the way we can do that is multiply on the left by A inverse. So let's call this matrix A. Let's call this X, and suppose this is B. Well, what I can do is multiply here by A inverse, and do the same thing on the right-hand side. And notice I'm multiplying on the left. Because what this does is makes these two the identity, multiplied with x, and we're saying that is equal to A inverse times B, and the identity times x will just be x. So we can obtain x just by multiplying A inverse with B. So that's exactly what we're going to do. is A inverse, this is B. This should yield us a column vector 3 by 1, because 3 by 3 by 3 by 1 matrix would yield 3 by 1. And we just perform the multiplication. Negative 8 plus 20 is 12, minus 10 is 2. 20 minus 32 is negative 12, plus 15 is 3. Negative 8 plus 12 is 4, minus 5 is negative 1. So this is saying x1 equals 2, x2 equals 3, and x3 equals negative 1. If we come back here, 2 plus 3 plus negative 1 equals 4, so that works. For the second equation, 2 plus 2 times 3 plus 4 times negative 1 is equal to 2 plus 6 minus 4, which is equal to 4, so that checks out. And then for the last one, we have 2 plus 4 times 3 plus 9 times negative 1, which is equal to 2 plus 12 minus 9, which is equal to 5, and that checks out. So we have solved our system of equations. And like I said, there's many ways to solve that system of equations. This is just one neat method to do it with inverse matrices, but there you go, that's your application of inverse matrices right there. You've learned how to compute them, and now you can use it to solve problems like this. So yeah, that's basically all I have prepared for today's lecture. I hope you enjoyed it, hopefully learned something new, and as always, take care. Until next time.